Thank you very much for the invitation to speak here. It's always a pleasure to be in Lumini. So, as I wrote, this is joint work with Pierre Colmez and Viesha Nijol, and this is very much in progress. And also I decided to give a talk about things that I do not understand, because this offered me a much wider variety of topics. So this is one of the things I do not understand. And so it will be about some very annoying problem that we encountered 2 years ago when we started to ask ourselves whether the cohomology of p-adic symmetric spaces has something to do with the p-adic local Langlands correspondence. And well, at least one of us considered that this should be a trivial problem, so I will talk about this problem today. It turned out that when trying to solve it, this problem was rather resistant to classical treatments, so we had to wait a certain time to have the right tools. And so the goal for today will be to explain how to use the A-inf cohomology theory of Bath, Morrow, and Scholze so this is, well, they have two papers so far, and we use both of them actually to describe the p-adic étale cohomology of Drinfeld spaces. So these are some very classical p-adic period domains, maybe the most classical ones together with the Lubin-Tate spaces. And a relatively natural question is to ask whether this p-adic étale cohomology can be described in some reasonable way, and the goal is to prove that this is the case. And strangely, it behaves exactly as in the L-adic situation, and I will try to emphasize at some moments what are the differences in the proofs. So before I can state the result, I need a certain number of notations. So this is a historical moment for me, because it's the first time I will not write G equals GL2QP, but G equals GLN of K. So I take D a positive integer, K a finite extension of QP, and G will be GLD plus 1 of K. And I need to introduce this Drinfeld space. Unfortunately, this is rather easy. So I write H dk, so this is Drinfeld's p-adic symmetric space of dimension D. So this is some kind of infinite hyperplane arrangement. You take the projective space over K, which you see as an analytic space, and then you delete all the K rational hyperplanes. And I will fix C over K, a complete algebraically closed extension. So for instance, if you look at H1K of C, this is C minus K, which has some obvious similarity with C minus R. So in general, one can show that this is a p-adic period domain, in the sense that it has some kind of modular interpretation. So these are rather standard spaces that occur when studying, for instance, the uniformization of certain Shimura varieties. And Schneider and Stuhler gave a simple recipe for the p-adic cohomology of these spaces when, of course, L is different from P. And what I'm interested here is the case L equals P. So I'll be more interested in the geometric étale cohomology, so let me write immediately. X will always be the base change of this Drinfeld space to C, so it has an action of this group G, and in particular, you have an action of G cross Galois of K bar over K on the étale cohomology of X with, say, coefficients ZP or something. You can choose your coefficients as you want. So the goal is to give a simple description of this object as a representation of this group. Now, how does it work? Well, I need to take some cohomological degree I between 0 and D, and to construct some simple object that is supposed to be a candidate of this one. Well, as usual in this story, you have Steinberg representations. So whenever you have P, a standard parabolic, of G with respect, say, to upper triangular matrices, you can construct a continuous, say, generalized Steinberg representation with ZP coefficients. So I'll not give the recipe, but it's a quotient of the space of continuous functions on the K points of the corresponding flag variety. So for each such standard parabolic, we have a certain representation SP of P of G. So these are very classical objects in the complex setup. If you take complex coefficients or if you take p-adic coefficients, they behave essentially in the same way if you take FP coefficients or QP coefficients, in the sense that they are still irreducible, admissible, and so on. So they are not so bad. Oh no, that goes up. What am I doing here? No. I'm always playing with these things without knowing how they work. Well, So in particular, if I look at my cohomological degree I can take the corresponding standard parabolic, which will be something like GL d plus 1 minus I, and then something like that. And this will give me a corresponding Steinberg, which I will simply call SPI. Right? So this will be our candidate for the answer. And now the main theorem is the following. There is a canonical G cross Galois of K bar over K equivariant isomorphism between, on the one hand, HI et al. Of X ZP twisted by I. So this is state twist. And this is the same as, well, you take ZP dual of this a generalized Steinberg representation if you are between 0 and D, and it's 0 if not. So the answer is very simple in the end. So before I discuss the proof of this theorem, which will be the main part of my talk, I want to make a series of remarks concerning this statement. So the first remark is that for L equals P, for L different from P, you have exactly the same statement. So as I said, this is due to Schneider and Stuhler. So the way they prove it, they study actually the cohomology of a natural covering of this space X. More precisely, they study the cohomology of things like that. You take projected space, and you take out finitely many epsilon neighborhoods of hyperplanes. And say coefficients, well, z over L to the k. Right, so this is the epsilon neighborhood of a hyperplane. And what they managed to do is to give an explicit description of these spaces. And the key point in their argument is that if you take the cohomology of a space cross a ball, there is a question? If you take the cohomology of the product of a space and the ball, you get the same thing as the cohomology of the space itself. So this is some you put trivial Galois action here. Yes. Yeah, maybe I should say this. So this is the key input in their work, which allows them to essentially get rid of this epsilon and to reduce to the case of an algebraic situation, in which you really have the cohomology of a usual hyperplane arrangement, and then it's a fairly involved combinatorial argument, but that's really the miracle that makes this object computable. This completely fails. In the p-adic situation. For instance, if you take X to be just a point, well, the p-adic cohomology of a ball is a complete mess, and of course it's not the cohomology of a point. So one definitely has to do something rather different in the p-adic setting. So for some time, people didn't really believe that such a simple, well, at least some people didn't really believe that such a simple result would actually hold, except that there was a rather amazing result of Drinfeld, who did the case d equals 1, in which he got exactly this formula in degree 1. Well, there are some gaps in his proof, but they can be easily fixed. And so he got this for I equals 1. And then for instance, if you look at H2 of that, you can show that this is 0 by using some results of Berkovich. And starting with degree 3, it's a general result, say in dimension 1, that the cohomology vanishes for such spaces. So if D is at least 2, let me just say Berkovich. Yes, sorry. D equals 1 and I equals 1, yes. And here D equals 1 and I is at least 2. Okay, another remark is that if you invert P, you can prove the theorem. And this is what we did before. Via symptomic cohomology. In other words, you simply forget about p-adic étale cohomology, use the Fontaine-Messing period map, and then it becomes simply a problem of computing the symptomic cohomology of these things, which comes down in the end to computing some crystalline cohomology and some de Rham cohomology, and you can do that by some suitable versions of the Hyodo-Kato isomorphism that holds even outside the proper case. So one remark that I should make, and of course I didn't, is that of course this space is not quasi-compact, and this is the main thing for which many of the tools do not hold.
Excuse me, what means symptomic?
Let me not go into that. I will never use this, so this is just a remark. Right?
Google,
Sorry?
Google
Well, no, you just have to wait for the next talk and you will have lots of symptomic things. So, so let me not say anything about this. Yes?
What is the definition of ZP cohomology? Some passage to the limit?
This is continuous in the sense of Janssen. I mean, it's not really inverse limit of the things with torsion coefficients. Yeah.
Goes into the sheet still.
Yeah, you have some R limbs on the left. But that's another point I want to make. You can actually get the result because now you know that this is a p torsion free. You can also get it for torsion coefficients. So. The most difficult part in the proof of this theorem is showing that this guy has no p torsion. Because once you know that, you could use the result when you invert p and you use some rigidity of lattices inside this guy with p inverted to get the corresponding result integrally. So really the key point here is how to show that this space has no p torsion. What else did I want to say about this? Yes, so I also want to mention that a natural belief would be that if you take pro-étale cohomology and say you put QP coefficients, that this should be well, it should be some kind of rational version of this guy, but this is definitely not the case, unfortunately. Should be, or fortunately, home from SPI into QP. So this is a very, very big space, right? However, this is completely false. Well, I mean, should be with this, because what is happening is that if you look at Schneider and Stuhler computation, if you put L here, then this is exactly what you get. I mean, the p-adic computation for pro-étale cohomology suggests that this is the formula that you should get, and unfortunately it is completely false. While for p-adic cohomology with integral coefficients, you really get the same thing as in the p-adic world. So the correct answer is that you have an exact sequence like this. In other words, what you expect to happen actually occurs as a quotient of the corresponding cohomology group. But there is a very big infinite dimensional C vector space sitting on the left. And this is a very big space, actually, much bigger than this one, for instance. So in general, you will see in Nigel's talks that for a fairly general class of spaces, one has some description of pro-étale cohomology in terms, say, of, well, Kyoto-Kato cohomology or, say, Durham cohomology to make it simple, and coherent cohomology. So, and of course, there are also some Banach-Kolmez spaces floating around. But in general, the pro-étale cohomology of these spaces is much easier to understand than the étale cohomology. And you may ask yourself, okay, what is the link between étale and pro-étale? Well, of course, you have a map from étale to pro-étale. This is not injective in general, even though it's not very easy to give a counterexample. However, in our case, it turns out that this is the case. But somewhat strangely, we cannot prove that this is injective without actually computing both of these guys. If you knew that this is injective, you would kind of win again using rigidity of lattices in this space. So again, it's a matter of, you have a natural map between étale and pro-étale. How do you show that it is injective? Well, since it's not injective in general, you have to do some work for this special case. So before I move to the proof, let me end with a remark that this is extremely misleading, actually. I mean, you see, the cohomology here is very nice. This is some dual of a very nice, irreducible, admissible representation. You can hardly imagine something better. However, already if you take dimension 1, things happen, interesting things happen only above level 0. So you see the truth only in higher level. Which means that you have to go up in the Drinfeld tower to see really what is happening. And unfortunately, once you quit level 0, things become very, very mysterious. I mean, we did some work for GL2QP, for instance, if D equals 1 and K equals QP, and we essentially described all finite dimensional Galois representations that map to H1 et al. Of the coverings for any covering of the p-adic upper half plane, and we showed that this realizes the p-adic local Langlands correspondence for certain Galois representations. So this is definitely not something that is going to be easy to handle, but it gives some hope that, well, at least you could get some nice candidates for this p-adic local Langlands correspondence. We cannot say anything with this kind of method in higher dimension. That's clear, and it will be clear from the method of the proof of this theorem. But the funny thing is that already in dimension 1 and for K equals QP, if you look at H1 et al. Of a covering, even the very first one, which is tamely ramified and cyclic, describing the full et al. Cohomology group seems to be a complete nightmare. I mean, it's not admissible, it doesn't have any reasonable finiteness property, and yet it has a very rich geometric structure. So this is the meaning of this vague sentence here. To see some really very interesting phenomena, you have to go up in the tower, and then things get really complicated. Okay, now let me discuss the proof of the theorem. So I'll spend some time explaining what doesn't work. I mean, how you don't prove the theorem, because actually it's very tempting to believe that this should be really trivial, and I'll explain why. But on the other hand, it really fails rather badly. So the most natural attempt is the following, is to use the ordinarity and the link with p-adic vanishing cycles, or nearby cycles, I don't know. So the point is the following. If you look at this rigid space X, or even the arithmetic one over K, this one has a nice semi-stable model X OK over OK. So I guess this was constructed by the linear via a functorial description, and it is reasonable to try to compute p-adic et al. Cohomology on a generic fiber via a computation of p-adic vanishing cycles. And on the other hand, quite a few things are known about the geometry of the special fiber of this guy. In particular, all the irreducible components are isomorphic as varieties, and they are just some rather complicated blow-ups of projective spaces, successive blow-ups. So they are not so bad in the end. The problem is that this is a very big space. So let me state a very beautiful result of Grosse-Kloner, which is really at the heart of our proof. It's an acyclicity result for the sheaves of logarithmic differentials on these spaces. So it says that if you take hi of, well, say x, which by definition is the base change to OC, and you take omega j, so as a convention, omega j is not the classical differential things. I have a semi-stable scheme, so I can put a log structure on it, and then I take really the logarithmic differentials on that. So this is really logarithmic. I don't want to put a log here because there will be an extra log after that, and I don't want to become an analytic number theorist with 2 logs, one after the other. So this is 0 for any I greater than 1 and for any j. And moreover, all global forms are killed by the differential. And you have an exact statement, an exactly similar statement on the special fiber. So, well, this is a very beautiful result, but unfortunately the proof is very involved. I really hope that someone in the audience can find a more natural interpretation for this vanishing result, because the proof as it is a very intricate combinatorial argument in which in the end you filter these guys reasonably well and you reduce it to the vanishing of the cohomology of some line bundles. So in some sense it is very geometric and natural, but implementing the thing is really a mess. So, but in any case, this is really, I mean, you will see in the proof this is really the key point. So once you have this result, the most natural thing you would like to say is that this implies, and it does actually, that Y is ordinary in Blockcut's sense. Well, I don't know if this notion is really due to Blockcut, but in any case it appears in their paper. So that means that if you take the cohomology of, say, Y, and you take Bj, so these are the closed J forms, that this is 0 for all I and j. And ordinary varieties, for instance, projective spaces, are very nice from the point of view of integral p-adic Hodge theory, because you really have exact statements. I mean, there are no constants involved in these issues, and you can do things in a very nice and uniform way. So you can hope that this kind of stuff would allow to compute the p-adic vanishing cycles. Of Y. So it's very natural from this point of view to try to do this. Now, you go and read Blockcut's paper and the way they prove this result, and you see that the very first line becomes wrong in our case. Because this is a statement that works very well for proper varieties, and it completely fails for non-quasi-compact varieties like ours. I mean, I recall you that this is an infinite chain of things, so this is a very big space, and there are some problems in exchanging limits and, I mean, direct and projective limits. And this is exactly the moment where everything breaks down in the argument. And it's really a pity because for some time we really struggled to try to implement this strategy because it's much easier and in some sense much more natural, but we couldn't do it. So now I pass to the more technical part of the story. So the Blockcut-Kyoto method, I mean, this concerns the proper smooth thing, and Kyoto did this in the semi-stable case, which is our setup, would imply an isomorphism of the form, you take the cohomology on the generic fiber, and this should be the same as H0 of Y, and you have some Drum-Witt guy. I mean, if you really follow their method, this is what you would get in the end. Of course, I mean, it's an even more special situation of the Blockcut method because with this extra vanishing result, you can actually kill all the cohomology groups in degree bigger than 1. So this is really what we expect. Now, Theorem, this actually holds, but only once you know the main result. In other words, indeed, the Blockcut method works, but for some very mysterious reasons. On the other hand, when doing this kind of computations, we realize that they force many cohomology groups being p-torsion free. And then, when listening to talks of Bad, Morrow, and Scholze, they nicely explained how the absence of p-torsion in the RAM cohomology, or say crystalline cohomology, implies absence of p-torsion in étale cohomology via this A-inf cohomology theory. So then it became rather natural to try to show the absence of torsion via this A-inf cohomology. So this is what we do. The nasty thing is that, again, if you look at the method of proof they have, is via some specializing things and some work with perfect complexes and so on and so forth. This again works only in the proper case. So this is not the method that we will follow, but the main ingredient is still their work. So now I move to the A-inf cohomology. So I should mention that I'm using this in the semi-stable case. So this is work of Chesnavicius and Koshikawa, who extended many of the results in BMS to the semi-stable case. So I will not assume that everyone is familiar with the A-inf cohomology. Everyone should be familiar with the symptomic cohomology instead. So let me make some very brief reminders about this A-inf cohomology and only what I need from it. So let me recall that there is this magic Fontaine ring, A-inf, which is the Witt vectors of the perfection of OC mod P, and that there is a natural surjection to OC, which is usually called theta, and the kernel of theta is generated by some non-zero divisor psi, which is explicitly mu over phi minus 1 of mu. And this mu will play a rather important role in the sequel. So this is the Teichmüller of a compatible sequence of p roots of unity minus 1. So this sits in A-inf. So I guess this is what is usually called Teichmüller epsilon minus 1 over this one. So this is the key setup from the point of view of ring theory, but now there is this spectacular result of BMS, which allows to construct some canonical complexes. So there exists a canonical deformation to A-inf of the Theorem complex, which I will call, well, actually, which they call A omega x. So, of course, this has nothing to do with our special setup. This works for any semi-stable p-adic formal scheme over OC, and X is just the corresponding analytification of that formal scheme. But I will only use it in our setup. So what does it mean that it's a deformation of this Theorem complex? It simply means that if you take quotient by this psi, of course everything is derived here. I mean, this is really a derived tensor product here. This is the Theorem complex. So this, I guess, is called the Theorem comparison. And on the other hand, there is a very nice link with étale cohomology. So one has canonical isomorphisms, or quasi-isomorphisms, between, on the one hand, you can take A omega, you invert this element mu, and then this is the same as the push forward of the relative Fontaine ring or sheaf A-inf, and you invert mu. And what is this mu? Well, it already occurred several times in the talks. This is the natural projection from the pro-étale side of the generic fiber to the étale side of the formal scheme. So you have this kind of comparison between this rather mysterious object and this one, but actually if you look at the construction, this is really kind of clear. And on the other hand, you have something like, well, I hope I'm not getting this wrong. This should be, so again, one has to be a little bit careful at the meaning of this Frobenius equals 1 here. This is really some homotopy fiber, but this is really an interpretation of the Artin-Schreier exact sequence, which is very classical in the story. Namely, you have 0 goes to ZP, goes to A-inf, goes to A-inf, and then goes to 0. So you just project this exact sequence to the étale side of the formal scheme, and you have this one, and this basically follows from the construction. But you see, there is something a bit annoying in here, namely the fact that you have to invert this mu. Now, when you are on a proper scheme, of course, if you apply R gamma, you can just take a mu outside, because it commutes with localization. But if you are on a quasi-compact scheme, on a non-quasi-compact formal scheme, then it's much more delicate to take the mu outside, and actually it doesn't hold in general. So this kind of description is not very useful. I know that there is some absolute bound for which, you don't really have to invert mu. You have maps between this one and this one, I guess, whose composite is some fixed power of mu. But even in that case, it doesn't seem to be very easy to handle the situation. So we're not going to use this canonical comparison result, which is in BMS1, but rather some kind of amazing integral formula that occurs in their second paper, and which is some kind of purely integral comparison result for symptomic cohomology, but written in this world of A omega business. So let me remind you how this works. So you want a very similar formula, but without inverting mu in this. And you also want to have a version in which you allow arbitrary Tate twists. Here, Tate twist is just trivial, it's 0 Tate twist. But I want something that involves also any kind of Tate twist. And it goes as follows. So the theorem. There it is stated in the case of smooth things, but it actually works in essentially complete generality. So it says the following: there exists a canonical identification between, well, on the one hand, you truncate this projection with Tate twist by I, and then, well, you do something very similar to that one, namely you take A omega, you introduce something that is called Broykissen-Farg twist. It's Broykissen-Farg or just Broykissen? Well, I guess it's Broykissen-Farg because there is A-inf in here. Then you truncate. Then you take fixed points under Frobenius, and finally you truncate again. Okay, it looks rather messy, but it has a very similar form, right? It's basically the same thing as here without having two comparison results and without having a mu inverted. So this is a Broykissen-Farg twist. Well, this is their convention. They invert phi. They work with the... Yes, but... Well, right. But at some moment, no, it's not the same thing, because here this is the right. So at some moment you have to take co-kernel of phi minus 1 minus 1. Well, I agree that this should be the same as the co-kernel. Yeah, you have some powers of psi, right? That because you truncate, right? You have to truncate to get... You have to truncate also because there are some powers of psi that come into.
But I mean, just if you take the bracket input a-inf1.
A-inf.
Only the phi inverse is integral.
Right, because you have to divide by mu to the I in the definition, right? But anyway, this is the correct. So Broykisenfart twist. Well, the upshot of this story is that if you manage to compute the cohomology of this A omega, in other words, if you compute the A-inf cohomology of the Drinfeld space, you get your hands on the cohomology of the Drinfeld space with ZP coefficients. Well, of course, when I say it's enough to compute, you also have to identify this operator when you do that. And now comes the really funny part. In general, it is, of course, essentially impossible to compute such an object for a given variety because this is supposed to compute via specialization the crystalline, étale, and the RAM cohomology. So there is basically no way you can do that. However, this formal scheme coming from the Drinfeld space is so special that we can actually give a formula for this. So the theorem is the following. There is a canonical G cross Galois. Well, let me put it like this. Cross phi minus 1, equivariant, isomorphism. So you have this ZP dual of the special representation. So now this is a compact ZP module. It's a profinite thing because SPI is a free infinite rank module over ZP. So when you dualize, you have an inverse limit of finite free ZP modules. You take completed tensor product over ZP with A-inf, where this one has the p-adic topology, which is the natural topology. And this is isomorphic to the one we want. So once you prove this result, you put in the machine this comparison result, and the rest is essentially formal. The funny thing is that once you have this, you also get for free, for instance, via these specialization results, you also get the cohomology of, say, omega j. You also get integral drum cohomology and the integral crystalline cohomology of these things. However, the problem is that you have to use all these results to prove this. So first of all, you compute everything that is related to coherent, crystalline, and so on, the RAM cohomology on the formal scheme. Then you use that as an input to construct this isomorphism. So now I want to explain the proof. Sorry? Well, there is a, I mean, there are all kinds of twists in here, right? And on the left, no, you just have this. Well, I mean, the phi minus 1 there is really phi minus 1 on A-inf. I forgot to say it, but Frobenius is invertible on A-inf, of course. Okay, so how does the proof work? Well, as usual, it works in two steps. Construct a map and show it's an isomorphism. Undergraduate technique. So how do you construct the map? So this uses a very nice idea of Jovita and Spies. So what they did was to find a very nice conceptual and explicit isomorphism from Schneider and Stuhler. I mean, the Schneider-Stuhler computation is a very abstract argument, very combinatorial, and in the end, it gives you some isomorphism, but it is definitely not explicit. Now, what they did was to make it explicit and show that this is really obtained by integrating Kummer symbols, essentially. And this is what we do here in the p-adic setup. So how does it work? Well, the key point is to interpret SPI dual as a space of measures on a suitable space Now, of course, you have one that is completely natural, because I remind you that this SPI dual naturally sits inside measures on the corresponding flag variety. Because by definition, the special representation was a quotient of the continuous functions here. But this is not what you want to do. So what you do instead, échanger des tableaux, ouais. Well, this is why I don't want to exchange boards. Non, j'ai pas des mains assez longues. Okay. So, I was saying that I want to interpret this as a space of measures. On what? Well, basically, the point is to look at the boundary of the space and to create a space of measures on the boundary. So this is some kind of Poisson transformation or things like this in dimension 1. And it's a vast generalization of this kind of construction. So this is due to Schneider and Stuhler. And I guess there is also some input from the linear, which says that there exists a canonical surjection from the space of measures on H I plus 1 to the one I want, to the dual of this special representation. So you see, instead of writing this one as a subset of a space of measures, I write it rather as a quotient. It's a very different perspective, but the point is that you can easily integrate along this space. So I remind you that this is the space of k rational hyperplanes in the projective space, right? So this would be something like P1 of QP if you are in dimension 1 and k is QP. And so naturally what you do then is to construct a map from measures on this space to the space you are interested in by integrating Kummer classes. So the Kummer classes a priori live in étale cohomology, but then you can use this comparison result to move to A-inf cohomology. So you have a map from étale cohomology to A-inf cohomology, so plus the map from HI étale to HI of A omega. And then you have to show that this map extends continuously to the completed tensor product, and this is how you get the corresponding map from here to here. Now the fun part is how you prove that this is an isomorphism. So second step. This map, well, did I give it a name? Yeah, this map, call it alpha. And I simply call this guy M, is an isomorphism. So now what we're going to do is to use both the de Rham specialization and the Hochstate specialization. So you argue modulo phi of psi. So not modulo psi. So if you want to show that such a map is an isomorphism, well, everything is complete for the phi of psi-adic topology on the left. It's definitely not clear that this module is also phi of psi-adically complete. I mean, at least not from the definition. There is no reason a priori. So one has to prove first that M is p psi-adically complete, and p torsion free, and also p psi torsion free actually. It will follow from the argument that it is also phi of psi torsion free. So I'll come back to this in a minute because this is a little bit annoying. So let me just take it for granted. And then you can actually argue modulo phi of psi using the integral Hodge-Tate spectral sequence. So what is this integral spectral sequence? Well, it's a spectral sequence for the hypercohomology of the quotient of this guy by phi of psi. So this uses the Hodge-Tate comparison, but really the integral one. Hodge-Tate spectral sequence, I guess this is H P X omega Q I minus Q, I guess. Now, this guy is 0 basically all the time by Grosser-Klone. This is where we use, finally, his acyclicity result. This is 0 unless p equals 0. So you deduce from this that the cohomology of this quotient is the space of global differentials on the formal model. Now, one has to argue a little bit, but it turns out that this is really M modulo phi of psi. And so, what happens in the end is that you have to understand the reduction modulo phi of psi of this map. So it is very easy to understand it on the left-hand side, because this is just the same dual completed tensor product with OC. It's more delicate to understand it on the right-hand side, but I have just done the basic work. The right-hand side reduced modulo phi of psi is just differential forms on the model. And this one can be computed. You see, this is why I said that you cannot actually get this kind of result from the main theorem, computing the A-inf cohomology, because this is some intermediate step in the proof of that result. So it can be computed via the same method. So instead of integrating Kumar classes, you just integrate d log of invertible functions, and you get OC, completed tensor product with SPI dual. And of course, you did a lot of comparison business in here. You used the Hodge-Tate spectral sequence. You used all kinds of things. So what you have to do in the end is to show that indeed the reduction of this map is the natural map you started with. In other words, you need the compatibility between Kumar classes and d log. And so that means that you have to go through the proofs of all these comparison things and check that in the end you have the beautiful commutative diagram. Fortunately, Scholze already did the hard work as usual. So he did it on the rigid analytic, I mean on the generic fiber. There he proved compatibility between Kumar map and d log. And so it's a matter of checking what is happening when you go from the formal model to the generic fiber. So it's a rather painful diagram chase, but there's really nothing very difficult in there. So what you do in the end is that you check that this natural map, when you reduce it modulo phi of psi, is just the natural map that you would get by simply integrated d log of invertible functions. And then you prove that this is really an isomorphism, but now this is a much easier problem, right? Because you don't have étale cohomology anymore. This is just coherent cohomology, and actually it's not very easy to get this result, but one can do it in a certain number of steps. And this is something that we have already used actually in the previous paper, which was dealing with étale cohomology, but with p inverted. So yeah, I guess I will stop here actually.
Are there questions? Okay, so maybe let me. Oh, sorry.
There's one from here.
Sorry.
Schneider's tool also give you the RAM community of space?
Yes, they give, but the rational Durham. I mean,
So you cannot add
the problem is that they don't give you the Durham cohomology of the formal model. They only give you the Durham cohomology of the generic fiber, and that is much bigger. But basically, we use that kind of result to go to this one.
So can you, I mean, so in this integral setting, you can also prove that the pro-étale cohomology is
Yeah, they are the same.
between étale and pro-étale is
Once you have ZP coefficients, they are the same.
no, okay.
When you put QP coefficients, one is much bigger than the other. But for ZP coefficients, they are the same.
Okay, so let's thank Gabriel.